All right. Once again, this is the start to our trig portion of the course. Um, when you deal with trigonometry, we deal with angles. When you're in geometry, you deal with a bunch of, we have one definition of an angle. When we get to trigonometry, we have a second definition of an angle. When we deal with trigonometric functions, we have what is called a periodic function. We deal with functions all the time. That's in the form of y equals, or f of x is equal to some equation that takes a value from the domain and assigns it to a value in the range. We're used to y equals 2x plus 3, y equals x squared plus 2x minus 7. Those are linear functions, those are those are quadratic functions. We've talked about polynomial functions when we're dealing with polynomials and finding roots of polynomials in the college algebra for the first part of this course. We have periodic functions. When we talk about periodic functions, these are function values or y values that will repeat over a certain domain. Okay, these are things that continue to repeat themselves. We can look at Mickey's big hand, Mickey's little hand on the clock. The second hand continues to follow a pattern. The minute hand continues to follow a pattern, but it will continue to repeat itself over and over again. Every day we have a sunrise, we have a sunset. Okay, the moons. We have the quarter moon, we have the half moon, we have the last quarter moon, we have the full moon, we have the new moon, we have all the different moon cycles. But every month that continues to repeat itself. Those are periodic functions. Well, when we're talking about trigonometric functions, the sine, the cosine, the tangent, these are periodic functions. They will repeat themselves over and over and over again. When we were in geometry, we had a definition. Okay, an angle in geometry was formed by two rays connected at their endpoints, and that was our definition of an angle. So we had one Ray, we had Earl Ray, we had Billy Ray, we had two Rays that are the Ray brothers. We connect them at their endpoints here. We form some angle. And that was our definition of an angle when we're talking about geometry. But in the geometric world, this angle, which we will symbolize by different Greek symbols, the value of theta, in geometry, this value of theta was between 0 and 180 degrees inclusive, which limits us to a specific domain, okay, a values of 0 to 180 degrees. When we talk about trigonometry, we change this definition, we get the big boy, big girl mathematics. It's used to measure the amount of rotation of a ray. How much rotation do you have of a ray? So we take this ray, rather than dealing with two different rays, we will still deal with two different rays, but now we talk about a single ray, and we rotate this about its endpoint. So we have the amount of rotation of this ray about its endpoint. So we hold the endpoint here, and we spin it around. Once again, this is like Mickey's big and little hand up there on the minute hand and hour hand on the clock. We hold it at the center, and we continue to rotate it around. We have an initial side. It's the point at which the angle of rotation starts. It's where we start our rotation, the initial side. You need to know where you start. And we have a terminal side. It's the point at which an angle of rotation stops. So you have an initial side, you have a terminal side. Where do you start your ray? Where do you end your ray? So if we talk about a ray, once again, we can talk about, we have an initial side. This is where we start. Okay, this is where we start. And we rotate this angle to a terminal side where we stop. And this is our amount of rotation. We have an initial side where we start our ray, and then we have a terminal side where that ray stops its rotation. Once again, think about Mickey's big and little hand spinning around the clock. Okay, we rotate in our hand, we rotate the minute hand around our clock. Okay, Mickey's big and little hand up there makes an angle of rotation that we have up on the clock right now. We form an angle. And this angle, once again, we use our Greek symbols, theta, alpha, and beta, to be able to symbolize this. These are variables for our angle of rotations. These are Greek symbols. These are Greek symbols. Once again, I will typically use the first one, theta, but alpha and beta will also join the party, the trigonometric party here. When we talk about a standard position, the standard position, there's 4 requirements for the standard position of an angle. The vertex of the angle is at the origin. Yeah, the vertex of the angle at the origin. The initial side of the rotation is on the positive x-axis. Clockwise rotation is negative, counterclockwise rotation is positive. So when we take a look at an angle here, we have an initial side on the positive x-axis. We have the vertex is at the origin. We have positive rotation. Positive rotation is clockwise rotation. Negative rotation, counterclockwise rotation is positive, and clockwise rotation is negative. So if I'm going to rotate 140 degrees, I'm going to have my initial side here. This is where my rotation starts, and I'm going to rotate this 90 degrees. This is 180, so it's going to take us into the second quadrant. So here's our rotation of 140 degrees. This is my terminal side. This is where it stops rotation. Once again, we start on the positive x-axis, pointing to the right, and our positive rotation is counterclockwise. Negative rotation is clockwise. What I want you to do here is I want you to draw 2 more angles, negative 140 and positive 420 degrees. Rotate those 2 angles. And once again, check your answers with somebody around you.
I got both.
Okay, negative 140. Where's our terminal side going to be for negative 140, Alex? third quadrant, where I have my initial side on the positive x-axis. I have my endpoint at the origin. We have to go negative, which means we're going to go clockwise. And we're going to rotate this negative 140 degrees. We do not need a protractor here. Do not need a protractor. Get a close enough for government work type of measurement in there. 140, we have 180, we have 90 here. So we're a little bit closer to the 180 degrees there. 420 degrees. Jacob, where is our terminal side with 200 or 420 degrees?
Quadrant 1.
Quadrant number 1, where if I rotate this, rotate it, 90, 180, 270, 360. This gives me 450. So I'm up here in quadrant number 1. So we have a rotation of 420 degrees. Here's my terminal side. Here's my initial side. Now, when you're dealing with geometry, your angles was bounded by 0 and 180 degrees. When we talk about angles now in trigonometry, we have unboundless angles here. So our angles can be anywhere between negative infinity and positive infinity. Okay, I could be anywhere from negative to positive infinity. I'm not restricted to 0 to 180 degrees. Reference angle. When we deal with a reference angle, a reference angle is a positive acute angle. And this could also be right, I guess. Formed by the x-axis and the terminal side of an angle. A positive acute, and that could be right. You can have a right angle here. That is formed by the x-axis and the terminal side of an angle. And what we do is we put a subscript R in there to refer to the reference. Sometimes you will see in a book theta REF. Okay, I will just use theta R, which is our reference angle. So what we're looking for here is, take a look here. The positive acute angle formed by the x-axis, and the terminal side. So if we take a look at the first triangle up here, the x-axis is a line that stretches the whole from left to right. So we need to be positive and we need to be acute, or right. So we look at the x-axis here and the terminal side. So we have the x-axis and the terminal side. Doesn't say the positive x-axis, just says the x-axis and the terminal side. This here is our reference angle, theta R. So if I take a look at theta R, my reference angle here, the x-axis and the terminal side, what's the measure going to be, Emerlyn? 40 degrees. And we can use our noggin here. Then if I rotate all the way down to here, this is 180 degrees. So I'm going to be stopping short of that at 140. What's my measure between 180 and 140? Go ahead and find your reference angle for the other two triangles, or other two angles. What is your reference angle? And once again, check your answer with somebody around you. David Newsbaum, what do you have for the first one? 40 degrees. Now this is still 40 degrees. Even though we have a negative here with a negative 140, common mistake here to say is my reference angle here is negative 40 degrees. That is a common mistake. And plus I'm rotating clockwise to get to that point. Okay? That is a common mistake. This reference angle is always going to be positive, so this will still be positive 40 degrees. Here's my terminal side and the x-axis here. What is my angle that is formed there? X-axis, terminal side, theta reference, last one, Jamie, would be what? 60 degrees. Because if I rotate all the way around one time, that's 360. We have to go an additional 60 degrees to get to the 420. Before the advent of calculators and the access to calculators, portions of angles were not used, or decimals were not used for portions or parts of angles. Okay, the advent of calculators has made life a little bit easier in regards to being able to calculate sine, cosine, tangent of specific angles and parts of angles. But before the advent of calculator, my days, and we're talking about old school, okay, when I was in class or when I was in the trig class in high school, I had to look up in a table the measurement of sine of 37.5 degrees or 37 degrees 30 minutes. There was portions or parts of an angle. The table was in angles, but it was also in what was called minutes and seconds. When you talk about minutes and seconds, these minutes and seconds are parts of angles. We deal with decimals quite a bit. When we have a decimal of an angle or part of an angle, we deal with it mainly in decimals. But the old school method is dealing with it in minutes and seconds. Well, the nice thing about minutes and seconds is it sort of follows the idea of hours. Because if I talk about 1 degree, this is equal to 60 minutes. How we symbolize that 1 degree, how we symbolize the minutes is we use a single hash. So 1 degree is equal to 60 minutes.
Sort of like feet.
Yep. And when we talk about 1 minute, well, in minutes, we take a look at seconds. There is 60 seconds in a minute. So 1 minute is equal to 60 seconds. How we symbolize the seconds is we have a double hash there. So we have inches if you want to refer to it as that.
But
Bless you.
I'm looking at a lot of blueprints. So it's just the way I see it.
So what we want to be able to do is we want to be able to, because our calculator, you can find in your calculator minutes and seconds. Okay, it is hidden somewhere within your calculators if you want to sit there and try to find it. Okay, to me, that's too much work. That's too much work. So I'm going to look to try to find an easier way to convert minutes and seconds into decimals, because I'm lazy. Okay, I'm a human. A human tries to find the easiest way to do things. Okay, the path of least resistance, sort of like water there, follows the path of least resistance. That's the same thing with respect to conversions of degrees and minutes into seconds or into decimals. I want to convert 27 degrees, 41 minutes into a decimal. What we want to deal with here is the 41 minutes. How do we convert that into a decimal? Well, if we take a look at a pizza that is divided into 4 pieces, and I eat 3 of those 4 pieces, if you eat 3 of the 4 pieces, how do I convert that into a decimal if I ate 3 of the 4 pieces? Amy? 3/4 as a decimal would be what? How did you get 0.75? 3 divided by 5. The portion that we ate over the entire portion of the pizza. So we had 3 out of 4, which is 0.75. Well, when we talk about this minutes here, we have 41 minutes. That is a part of the degree. 41 minutes is a part of the degree. So I want to convert that into a decimal now. Well, the part is 41. The entire degree is how many minutes? Yeah? 60 minutes. So we have 27, and then we have this 41 divided by 60. Now what we can clickety-clack to our calculator is this is 27 degrees and 41 minutes. So what mathematical operation do we have? Addition. So in our calculator, I can clickety-clack 27 plus 41 divided by 60 and hit my enter. And we can come up with a decimal equivalent.
How far do I have to go?
2 decimal places is fine. What do we come up with, Anna?
27.68.
Well, if I take a look at minutes and seconds, we have the 57 there. The 21 minutes we can deal with like that. But how do I deal with the seconds?
You put over 3,600.
Why 3,600?
That's 60 squared.
Okay. How many seconds are there in a degree? Well, how many seconds are there in an hour? Okay. Think of it that way. Well, there's 60 seconds in a minute, and then 60 minutes in an hour. So we have 60 times 60, so we have 18 divided by 3,600. So once again, I can clickety-clack into my calculator, 57 plus 21 divided by 60 plus 18 divided by 3,600. You can type it in, you can clickety-clack in as is. Your calculator will follow orders of operation for you. Seth, what do you come up with?
57.355.
Wait, what?
355.
355. Okay, we will stop there today. Tomorrow we will convert the other direction. You'll be able to do the back side of the homework. Just worry about the back side of your homework here. Adios, and have a good day. Welcome back. Welcome back.
Oh, yeah.
Just you need to see how well we edited together. You fall out. I was just talking to you. You're like,
Worry about the back side.
It sounds like something got like lit on fire and tossed off a cliff. You can obviously tell if you get it. Yeah, it's like so much different.
Just worry about the back side.
You mean that one's